Okay, now we can verify by experiments that we'll do to pretty good precision in this lab that F net is proportional to acceleration. Okay? And we put an arrow over F net to indicate it's got a direction, and the acceleration also has a direction. And since proportional to means it's just a constant multiple of, a vector is in the same direction as a vector. So the acceleration's in the direction of the net force, which gets confusing if you're moving something in this direction and have a force in this direction, as with a car going around a circle. You have an acceleration, but you're not changing velocity. Something we'll talk about, like I say. Okay, so net force is proportional to acceleration. Can be verified to any degree of precision that we're capable of in the lab, and we'll probably do that in our next lab session. Okay? So, also, for given net force, acceleration's inversely proportional to mass, meaning if I apply the same net force to twice the mass, I get half the acceleration, just and so forth, okay? If it's 10 times the mass, I get 1/10 the acceleration. That's what this says, okay? Now, there's a problem here. This is a vector and this isn't. This has direction, mass doesn't. So really, I kind of lied when I wrote this down. Got to do something. This is the magnitude of the vector, how big it is. Its absolute value, sort of. And when we talk about vectors, we'll talk more about magnitude. Okay? Just how many units of acceleration do you have, regardless of the direction?
What exactly is force?
Huh?
What exactly is force? How do we figure out the force on our object?
We're getting there. We put these two together. And force is something that, okay, you asked, okay? Forces accelerate masses and or deform objects. Not a formal definition, but it's pretty close. You want to state it a little more carefully, a little more elaborately, but I don't want you to lose the idea within the elaboration. Okay, so that's what forces are. And you've measured forces by deforming rubber bands. Okay? And you've observed systems already that are accelerated by forces. Pendulum being one of them. You've used pendulums. Now the rotating beam Now that's not a point mass, it's a connected, you can think of it as a connected set of point masses. Set isn't exactly the word I wanted, but I couldn't think of the best one, okay? Okay, so anyhow, coming back to this now. If I write A without the arrow over it, that just means the magnitude of the acceleration. And the magnitude of the acceleration is inversely proportional to the mass for a given net force. Combine. This tells us that A is directly proportional to the net force divided by the mass. Since A is directly proportional to the net force for a given point mass, for a mass that isn't changing, and if you change the mass but don't change the net force, the acceleration is inversely proportional to mass. Acceleration has to be directly proportional to net force and inversely proportional to mass. Now, just make a side comment. Another thing that our curriculum does an absolutely awful job with is the idea of proportionality and variation. Okay? Now, there's actually sort of a reason for that. For some reason, this is difficult for most people at high school age to grasp. It's mathematically very simple. And I'm not sure why that is, because I know I grasped it in 8th grade. Now, I'm smarter than most of the people in my class, but my 8th grade math teacher kind of emphasized it, and I think most of the class had a pretty decent understanding of it. So I really don't know what's going on. My own direct experience is it ain't all that hard. Okay? But we had to build it up step by step, and you have to take a little time to do it, and everybody's too busy suppressing geometry to do that. That's not really what's going on. I still don't know why geometry is being suppressed. It's so important. Okay. Maybe it's just being suppressed because it's hard. So we don't want to make anybody do anything that's hard, do we? Okay, well, anyhow. I can't help editorializing once in a while. Okay. So kind of put proportionality and variation in your list of things to either review or learn. It's not hard at all. I was able to teach it very effectively in a fairly short time to liberal arts math students. Our quantitative reasoning now, sub pre-calculus level. It's not really sub. There's a lot more math in that than there is in pre-calculus. Okay, it's really good stuff. But it's generally taught to people who've not been very successful in their math. Not successful enough to do a pre-calculus. You can teach it to them. Whether they incorporate it to the depth to understand this argument might be a different question. Okay, so anyhow, you draw this conclusion. Now, what's it mean to be proportional to? It means it's a constant multiple of. Okay? And that constant multiple is the proportionality constant. Then the acceleration is net force divided by mass. Because to say this is proportional to is just to say that this equals some constant number times this. That constant number is the proportionality constant, and I make the proportionality constant 1. So whatever units you're measuring, be it meters, kilograms, and seconds, or pounds and slugs in seconds, or domino weights or masses, and whatever unit of length you want to use, this still holds. More familiar. More familiarly, net force equals mass times acceleration, which is not the way it gets reasoned out if you think of experiments you have to do, but that's the way it's usually expressed. So, and what do we call this statement? Any literate high school graduate should know what this statement is. And General Mattis, in a recent article, said anybody who hasn't read hundreds of books is functionally illiterate. Okay? Most people your age are functionally illiterate.
All right.
So if you're illiterate this way, okay, but fix that. Work on the book thing over your next 10 years or so. Okay? You're getting all your information from Facebook and internet blurbs and Twitter, you're going to be functionally illiterate. And if the only books you read are the ones you're required to read, you're not going to read them right in the first place. Get into some substance. You got to get into other people's thought and be able to develop your own. Again, just an editorial comment. But the same, an analogous comment goes with physics, okay? The fact that high school graduates come out not knowing this and not knowing that it's Newton's second law, it's criminal.
I thought it was one of Newton's laws, but I'm like, that's too simple to be one of his laws.
Huh?
I thought it was one of his laws. But
It's the second law. Yeah, well, I mean, so you're getting there. You're almost literate. I think you're pretty literate with this stuff, actually. Really, I don't care which law is which as long as you know what they say. Okay? And we'll quote the other laws as we need them. Well, if we put all this together with what we know about the pendulum, and I'm developing the whole thing of the pendulum a lot more than I intended to, but once I get started, I go where it takes me. Okay? Try to read your faces. Most of you are still conscious. Some of you can still write, so you do pretty well. Okay? We conclude. For the pendulum, again, F net equals negative kx. I'm not putting arrows over it, although probably should, but now we're just talking about things that are in the x direction. So we're really just talking about a force in the x direction that might be positive or negative, which actually does make it a vector. We're not going to write it that way. It was negative kx, okay? We want to do some calculus with this. We don't want those vector arrows over it. That introduces complications that justify a little bit of sloppiness in our notation, okay? Okay, so we have F net equals negative kx. And we have F net equals mass times acceleration. What can we conclude from this and this? Put these two together, what can you say? Go ahead, you started.
Mass times acceleration is equal to negative kx.
Yeah, there are two things that are equal, the same thing are equal to each other, and, you know, hopefully you kind of remember that. And I'm sure you've used that, just intuitively without even thinking about it. Okay, so we get mass times acceleration equals negative kx. So that acceleration is equal to negative k over m times x. Make sense? Now, how is acceleration, what is acceleration here? Well, motion is in the x direction, right? Now, so I'll write some side comments over here to justify the next step. Right? Velocity is the rate at which the position changes. Velocity is a derivative of position. X is your position. X is a function of t. So your velocity is a derivative with respect to time of that function. It's the rate of change of your position with respect to time. And what's acceleration?
dv over dt.
Yeah, acceleration is the rate at which velocity changes, right? So I'm not going to write out another comment on that. So that's dv dt. And of course, v is dx dt, so it's a derivative with respect to t of dx dt, which makes it what? Huh?
The derivative of velocity.
That's what it is.
The second derivative.
Second derivative of x with respect to t. And you know that. Just wanted to give you an opportunity to think it yourself before I told you. Okay? Now, everything I've done up to here is not calculus. Okay? So now I've got a short interlude of calculus
Right.
that leads us to a lot of other stuff. Okay? And the calculus is going to be this. In shorter notation, I'm going to use the prime notation. Okay? Velocity is x prime, a is v prime, which is x double prime. The advantage to the dx dt notation is that you know that you're doing a change of position with respect to time. When I use the prime, you've got to know what you're doing it with respect to, right? Since we've defined this, these as functions of time, then implicitly these are time derivatives. That's going to be important. Okay, so we get this really important equation. A is just x double prime plus k over badly written m times x. I'll try to correct that, but I'd smudge it, and you know it's going to be m. Okay? Okay, that makes sense? Okay. Well, now we've got to solve that equation for x. Got to find a function whose second derivative is a negative multiple of itself. So think for a minute. What kind of function has a second derivative that's a multiple of itself?
Is that a